Okay, I'm going to go ahead and start with chapter 9. Chapter 9 is all about thermochemistry. In the world of chemistry, thermochemistry is an area in chemistry where we're looking at thermal, and thermal here stands for energy. And then chemistry here stands for, of course, the chemicals, right? So we're looking at chemicals or chemical reactions that release energy or absorb energy before the reactions actually go into completion. So it's very important to understand that in the previous chapter, chapter 8 ended with redox reactions. And through redox reactions, we were able to understand that chemicals are the source of electrons, and therefore chemicals are the source of electricity. So redox introduced us to the relationship between chemicals and electrons, or chemicals and electricity. Okay, so this chapter has us focusing on the relationship between energy and chemicals, chemicals and energy. So we're going to be looking at the movement of energy between chemicals. At some point, we'll be looking at the macro level, particulate level, and we'll call the chemical systems or surroundings. So let's go ahead and get started. Since this chapter is all about energy and energy movement, we'll start off by defining energy, the nature of energy. We're told here energy is anything that has the capacity to do work. Think about it. When you are tired, you say, I don't have enough energy to get this work done. I don't have enough energy to finish my homework. I don't have enough energy to study, right? Or I don't have enough energy to show up to class. I know I'm picking on you guys. Anyways, we relate energy to doing work. So we're told here energy is anything that has the capacity to do work. So if you're able to accomplish work, then you do so because you have energy. It says right here, think of energy as something an object or a collection of objects can possess. Since thermodynamics is all about the movements of energy, remember, even though we're covering thermochemistry, thermochemistry is one of those categories of thermodynamics. And thermodynamics is all about the movement of energy. So we have movement of energy between one system and the other, or the system and the surrounding. So we're told here, since we're dealing with thermodynamics, energy can be exchanged between the objects through contact. So we're talking about system and surrounding. While we're here, we're going to go ahead and define work. Work is the force acting over a distance. I remember being in physics and learning that work was acting perpendicular to distance. But as long as we can apply energy or force to an object and cause that object to move a certain distance, that is defined as work. So you apply work, or you apply force to an object and cause that object to move a certain distance. That is defined as work. What about heat? Heat is the flow of energy that is caused by a difference in temperature. So if you have two objects, one object in direct contact with the other, one object has a higher temperature. So I'll give you guys an example. Say it's at 100 degrees Celsius. The other one is at 20 degrees Celsius. Because of the difference in temperature, heat will flow from the hotter object to the colder object. So we want to make sure we define this early on. So we'll talk about this down the road. Classifying energy, we have two main types of energy. We have kinetic energy and we have potential energy down here. So I'm going to give you guys the bottom line here. Kinetic energy is the energy due to motion. So when we look at kinetic energy results because something is moving. So an object has enough energy, and the energy that allows the object to move, that energy is called kinetic energy. Okay? Then when it comes to potential energy, the object is not moving. The object is actually absorbing energy and storing that energy. So potential energy is usually either stored energy or energy due to position. So in the world of chemistry, we don't address this definition so much. We focus more on stored energy, energy inside of bonds, okay? So we tend to focus on stored energy. The energy inside the structure of a compound is essentially its potential energy. So I'll skip over this part because I feel like this part applies more to physics and nothing personal against physics. I am not looking at that right now. We're focusing on chemistry. So while we're seeing different forms of energy exist in life, we are focusing on the two main forms: kinetic energy due to motion, potential energy due to position or composition. Once again, in chemistry, we shall focus on composition, okay? Example of this kind of energy here, we have for kinetic energy, we have thermal energy when you have flow of energy. Associated with temperature difference, you have chemical energy associated with bonds and the positions relative of electrons and the nucleus. So I'm going to go ahead and move over to the examples. So we have examples of energy. Electrical energy happens to be an example of kinetic energy. Why is that the case? You have to show with kinetic energy that something is moving, right? So what is moving over here? In electrical energy, we have a flow of electrical charge. When you have a bunch of electrons moving from one place to another, usually we'll learn this in 1412. What causes the electrons to flow tends to be a potential difference or a difference in charge. So electrons that are flowing tend to generate what we call electrical energy. And so that is called, that's an example of kinetic energy. I feel like I'm using the word to define the word, right? But when we have a flow of moving electrons, when we have a bunch of electrons moving together, they generate electrical energy. So electrical energy is an example of kinetic energy. In heat energy or thermal energy, the presence of this energy causes molecules to move more, right? So molecules that were at rest will now move more. When they're moving more, this movement results in kinetic energy. So thermal energy causes molecules to move. So once again, in kinetic energy, you have to show an association between the energy and movement, okay? Now we're moving over to light or radiant energy. With light or radiant energy, what we're seeing here is I'm in a room right now that is lit. So the light I'm experiencing from the bulb is caused by electron transition. So we mentioned this back in Bohr's model, right? Bohr's model talked about the electrons being on different energy levels. And when the electron was on a higher energy level or that excited state, and it was going down to its ground state, the electron released the energy it previously absorbed. And that energy that we saw, if the wavelength of the energy released, or if the wavelength of the light released matched that of visible light, what we saw was light. Let there be light, right? And so electrons moving from one energy level to another tend to release light. So once again, we're seeing transitions here, which is synonymous with motion. They're moving from a higher energy level to a lower energy level, okay? Now, in the nuclear energy, we're now dealing with the nucleus. And in the nucleus, the atoms aren't necessarily moving. So any energy in those atoms, or so I shouldn't say in the atoms, in the particles inside the nucleus, the energy is stored. So nuclear energy is technically potential energy. Now, if something causes the atom to split or to explode, then you have potential energy being converted into kinetic energy. But until then, nuclear energy is stored energy. Now, it can be used in the future, but it's essentially stored energy, okay? And then we're looking at chemical energy, or, energy in bonds. And these are essentially potential energy because unless the bonds are being broken to accomplish something, the energy inside the bond is stored, and therefore it is potential energy, okay? So you're free to read further on this. I want to go ahead and go through this chapter real quick. Okay, when it comes to units of energy, in general, energy is reported in joules. Now, you can have metric prefixes such as kilojoules, but the idea here is energy is usually reported in joules. So when we see the unit joules, we know that joules or kilojoules. We know that we're dealing with energy, okay? Joules is also equal to kilogram meter squared per second squared. So the way I remember this right here is by using the kinetic energy formula, which states the kinetic energy is equal to 1/2 the mass of the object times the velocity squared. The unit for mass, at least the SI unit, is kilograms. And then velocity is meters per second. When you square that, you get meters squared per second squared. So 1 joule is equal to kilogram meters squared per second squared, if I can write correctly. Okay. And that's essentially the units of energy. Okay. Let's go ahead and move on and see what is going on down here. You want to be aware of the common units besides joules. Energy is also measured in calories. Now, there is a lab version of calories with a small c, or I shouldn't say underscore. Yes, lowercase c, that's calories. And then there's a food calorie that's written or measured with uppercase C. So 1,000 of the lab calories is equal to 1 food calorie. So in the food calorie, manufacturers are able to write the calorie with a capital C or uppercase C, and that indicates it's 1,000 times. So essentially, if you're eating a Snicker bar and the Snicker bar is 250 food calories, what you're actually eating is 250,000 regular calories, okay? And you wonder why it takes us hours in the gym just to burn calories, because what we're actually burning is a lot of calories, right? Okay, so I'm going to go ahead and move on. So over here, you want to make sure you take some time to write down the common units for energy besides joule. Joule is the most common ones, but sometimes in different areas, you will be required to convert from joules to calories. So you use this conversion right here. Or you may be asked to convert from joules to kilocalories or food calories. Well, food calories or kilocalories, you use that conversion right there. Or you may be asked to convert into kilowatt hour, right? Y'all, let me tell you when kilowatt hour became real for me. That became real for me whenever I graduated undergrad. I got my first apartment. I was so happy. I felt so grown. And then I was told I had to set the electric bill. So I'm like, okay, great. Well, you know what? I've always been a little bit different, special. Well, let me put it this way. I didn't have money, so I had to be frugal. Right. I didn't have a lot of money. So I did try to find, ways to cut costs. And one of those was that kilowatt hour. When I saw how much I was paying, I knew conversions, right? Cost per kilowatt hour. So back then I remember at some point it was 9 cents, right? Can be that way, or you can say 9 cents. 9 cents per kilowatt hour. So I had to do the math to figure out how much I was going to pay per month. It was crazy, y'all. But I realized that kilowatt hour made a difference ultimately in my budget and how far that money could stretch. So if you have no idea what a kilowatt hour is, that must be nice. That means you're not paying electricity bill, right? But when I graduated undergrad, I knew I until then I didn't know what it was. But when I graduated, I knew what it was, right? Because every month I'll get a bill saying, you use so many kilowatt hours. I'm like, no, I didn't. And then I had to pay for it. Anyway, moving on. So in the world of thermodynamics, there are certain rules that govern the math we do and certain rules that we observe, okay? The first law of thermodynamics is the rule that we're going to be looking at. And this law is about conservation of energy. So once again, we're being reminded, thermodynamics is the study of energy and its interconversions. Energy being transformed or transferred from one system to another and transformed from one form to another, okay? So in this law, we're told the first law of thermodynamics states, it's the law of conservation of energy, which states that essentially in a chemical reaction, the total energy in the universe is constant. So we're told here, this means that the total energy of the universe is constant. In a chemical reaction, oh my goodness, I just blanked out. The total change. Okay, so let me do this over again. I can do this, okay? So we're told that in a chemical reaction, the overall change of the energy of the universe is zero because energy of the universe is constant. So change in energy of the universe is equal to zero because energy is neither created nor destroyed. Now, oh, let me write that down here. Energy is not created or destroyed, but it can be converted from one form to another. So let me write that down. But can be trans. See, I get all excited and I started writing and misspelling stuff. Transformed from one form to another. Okay. And this is in the context of a chemical reaction. So in a chemical reaction, we understand that we are not creating new energy that wasn't there before, and we're not destroying the currently existing energy. All we are doing is transforming it from one form to another. Okay. And this is a paraphrase of the first law of thermodynamics. So in the universe, there's going to be no net change in energy. If you measure the energy in the universe 100 years ago and then try to compare with the one today, the amount of energy is the same. It is essentially constant. Okay. So before we continue with this part, we're going to define system and surrounding. Thermodynamics sometimes has a macro level view. Okay. Now, at some point, I mentioned to you what macro was. Macro usually means big. It's kind of like at some point in time, mega meant big. I remember back in the days, if you wanted to communicate something was large, you're like, oh my goodness, this is mega, right? So in the world of science, or the world of economics, I've heard that term a lot. They say, well, that was the macro level view. All it's saying is like you're looking at things in the big picture, right? You're kind of taking a step back and observing things. Thermodynamics tends to have that macro level view. Thermodynamics. Okay? Where we're saying the universe is essentially made up of two parts, right? So we don't overcomplicate things. The universe is made up of the system plus the surrounding. Now, as a student, I struggle to see the macro level view because my teacher one time accused me of being too detail oriented. Like I was nitpicking and stuff. I'm like, no, I'm not. You are. But he was right. I understand what he was saying. He was saying that I was too focused on the little things that I didn't really have a macro view of things. Okay. So thermodynamics, the view sometimes is macro. And so when we're looking at the universe that we said in a chemical reaction, the change in energy of the universe equals zero. This is the universe we're referring to. The system can have an energy change, right? The surrounding can have an energy change. But when you sum up the energy change, we're supposed to get zero. Okay, before we get all caught up in that, what is the system? So let me backtrack a little bit. Look at me getting ahead of myself. What exactly is the system? We're told right here, the system is defined as the part of the universe. Remember, the universe has two parts, right? The system and the surrounding. The part of the universe that we are actually studying. So if it's a chemical reaction we're looking at, that chemical reaction, that is the system. Then what is the surrounding? The surrounding is the other part of the universe, right? That is everything else in the universe with which the system can actually exchange energy. Okay, so we have a system right here. Inside the surrounding, no pun intended, the surrounding surrounds the system. Y'all see how I did that? Surrounding surrounds the system. So if the system and the surrounding are supposed to exchange energy, then together they make up the universe, right? Whatever the system loses, the surrounding gains. Whatever the surrounding loses, the system gains. They have that yin and yang relationship, right? That codependent, like they depend on each other. For the system to have energy, it has to get it from the surrounding. If the surrounding wants energy, it has to get it from the system, because according to this thing that we're studying, this universe, there's only two things, system and surrounding. Okay? So we kind of summarize this again. Thermodynamics is the study of energy that is exchanged between the system and the surrounding. Because in thermodynamics, we're focusing on that universe. What's the universe? System, surrounding. Okay. Okay. So we're told apparently energy can flow from the system to the surrounding. I already explained that here. If that happens, then the energy of the system drops and the energy of the surrounding increases. That is called exothermic. So y'all, I have an active imagination. Let's call it active, okay? And when I was a student and I was learning all these words, I'm not big on definitions because I tend to fixate. Remember, I was a detail-oriented person, right? I tend to fixate. So when I hear a new word, I want to make sure I really understand it before I move on. So I'm looking at this saying exothermic. I'm thinking, well, when we're defining that, what's the point of view from the system or the surrounding? It's important to realize in this section here, if your mind is unique like mine, that has to be defined. The default here is the system. See, because that's the part that we're focusing, right? We're focusing on. I'm laughing because I guess I missed that as a student. Anyway, the system is what we're focusing on. So most of these definitions and these conclusions are from the point of view of the system, not the surrounding. Does that make sense? Okay. So we have a system right here, and our system is SYS, and we have a surrounding the system. Let's say the system is losing energy. So let me give the system initial energy. So let's say this system here had 50 kilojoules of energy in the beginning. In the end of the transformation, it now has 20 kilojoules of energy. Okay. Let's say the surrounding had 10 kilojoules of energy. Based on what's happening here, since the system lost 30 kilojoules of energy, guess who got it? Because there's only two in the universe. This 30 kilojoules of energy was given to the surroundings. The surrounding now moves up to 40 kilojoules of energy. Because remember, thermodynamics is all about the system giving to the surrounding and vice versa. They're giving energy to each other, right? Since the system has now dropped in energy, we will call this exothermic because we are focusing on the experience of the system, not the surrounding. Now, sometimes the questions will ask you about the surrounding, but the author has to be clear because our focus is the system more than our focus is the surrounding. Our default focus is the system, okay? Hopefully that makes sense. Okay. And then in endothermic, once again, endothermic reaction, in this case, now the system is the one gaining. So the system starts off all innocent, 50 kilojoules. And then the surrounding, let's say, starts off at 10 kilojoules. If the system is gaining, the surrounding has to give to the system. In this case, the surrounding will give up, let's say, 5 kilojoules to the system. Let me draw it like this. So it gives to the system. So surrounding has to drop to 5 kilojoules, while the system now gains 5 kilojoules and becomes 55 kilojoules, right? Because it added 5 kilojoules. This one here lost 5 kilojoules. I guess I should write it that way. Why did I think about that? Okay, so back here, right? This one here added, no, it's subtracted. So it lost, I'm making this up as I go. Bear with me. This one here lost 30 kilojoules. That's the same thing as minus. So if you're doing accounting, that's the same thing as minus 30 kilojoules. And this one here will be plus 30 kilojoules, okay? So now let's go back and put these numbers. I'm just gonna put the second set of numbers in the first law of thermodynamics, right? In the first law of thermodynamics, the change in energy of the universe equals 0. Let's see how that plays out. Well, here the change in energy of the system plus change in energy of the surrounding must equal change in energy of the universe, right? And here we're told it's zero. So let's see how it plays out. In the second example here, the endothermic, the change was this part here. The system gained 5 kilojoules of energy. The surrounding lost 5 kilojoules of energy. So when you add them up, you get what? 0 kilojoules. Okay. This is true of endothermic reaction. I mean, if we want to just kind of go ahead and prove the same thing for exothermic reaction, I don't want to add a page here, so I'm just going to try to squeeze everything here. In exothermic, this time the system lost 30 kilojoules of energy, so minus 30 kilojoules of energy. And the surrounding gained 30 kilojoules of energy. So when you add these two, you get 0 kilojoules. So regardless of whether you have an endothermic reaction or an exothermic reaction, in the end, the universe remains constant. The change in energy in the universe is the same. Okay? That is essentially the law of thermodynamics. Okay, this example right here, we're pushing the ball and letting it come up. This is an example of physics problems, right? Once again, nothing against physics. Shout out to physics, but we're not studying physics here. Okay, so we're going to focus on the chemistry example. We're looking at energy transfer. In this picture, the purpose of this picture is knowing how to interpret what you're seeing. This, once again, is illustrating the first law of thermodynamics, where delta E is equal to 0. There is no change. There is no net gain of energy. The energy in the universe is constant in a chemical reaction. Okay, so here they're using energy gauges to track the energy changes in the system and the surrounding, or at least to communicate to us the value of energy, right? So before the system transferred energy to the surrounding, this is the system here and this is the surrounding here. So in the beginning, how about I give units to this? Because I feel so weird not having units. We'll call this 2 kilojoules. How about that? Because it's like right at 2, right? This is 1, 2. And we'll call this 1 kilojoules. So before any energy was exchanged, this is a surrounding is a 1 kilojoule, system is a 2 kilojoules. And then you have the exchange right here with the arrow. The exchange happens. When the exchange happens, now what do we have? The system went from 2 to 1 kilojoule. Therefore, the system has a change of, the change is final minus initial, minus 1 kilojoules. The surrounding went from 1 to 2, so the surrounding goes from 2 minus 1. Change is plus 1 kilojoule. So just like before, when you look at the change in energy of the system plus change in energy of the surrounding, the system drops. So that's minus 1 kilojoule. The surrounding went up. So that's going to be plus 1 kilojoules. Okay, just like before, the change in energy of the universe is 0. Okay, first law of thermodynamics. Okay, now we're moving on to what we call internal energy. So we're told right here, internal energy is the sum of kinetic and potential energies of all the particles composed inside a system. Okay, so sometimes when I was learning this, there are parts I felt I couldn't connect to because we weren't talking about humans. We're talking about systems and surroundings, and everything felt so abstract to me. So I would bring myself in the story whenever I could. So I thought to myself, if I were the system and I had kinetic energy because of the stuff inside my body that's moving, and potential energy because I have, chemicals and stuff. I have fat that stores energy and all these, molecules in my body storing energy. So I was made up of both kinetic and potential energy. And of course, you have the exchange, right? So we're looking over here. If you sum up all the energies inside the system, that's essentially the total internal energy. Okay. So I forgot to mention this. I was just thinking about it. To go from potential energy right, to kinetic energy, there has to be some kind of mechanism to convert that, right? We know that in our bodies, when we eat food, the food that we're consuming is essentially in a potential energy state. I mean, we chew it and we swallow it. But then we go through a whole process of metabolism where our body then becomes that device that uncodes, or not uncodes, decodes, that's able to harvest the energy. So you need to have a device to harvest the energy, or else the energy will stay forever in the potential energy form, right? So our bodies in this story, body is a device that harvests all the stored energy and converts it into a useful form, which is kinetic energy, okay? Doing important stuff in our bodies. Okay, so when it comes to a battery, I'm trying to make a point before I move on. With a battery, sometimes you have like some kind of device, a machine that can pull out the energy from the battery. In the case of a car, right? You have an engine that can pull energy from the battery in the car. So you get what I'm saying, right? Okay. So back to internal energy. As we're talking about internal energy, we're told here that the change in internal energy, and by the way, internal energy has the symbol E. So internal energy has the symbol E. Change in internal energy is delta E. So we tend to write this as a delta as in change, E internal energy. We're told that this value here is the state function, okay? The change in internal energy of the system only depends on the amount of energy in the system at the beginning and the end. So to try to make sense of this, I'm going to make up some numbers, okay? So let's say this is time equals 0 seconds, time equal 5 seconds, time equal 10 seconds, time equal 20 seconds, okay? So this 20 seconds will be defined as the end. And the issue is not really about time. Technically, time is not controlling the outcome, but y'all, I'm just trying to find some kind of rhythm to this, right? So you know what? Let me take away the time factor, because we have a chapter where time is important, and that's the rate chapter, and that is 1412, and we're not getting into that right now. But let's say this. Let's say measurements. So measurements. So we're going to take measurements, okay? And we're going to find E values. So for the first experiment, we measure the first E value, and the first E value is, let's say, 0 joules. We measure another value of E. So let me write this. Yo, I'm sorry, I'm making this up as I go. So sometimes it doesn't come out as great as I want it to come out. So the first E value is 0 joules. Second E value is, this is the first experiment, right? Second E value is 5 joules. Third E value is 10 joules. Fourth E value is 20 joules, okay? So we're doing an experiment and we're noticing the change in energy, internal energy. So it starts up from 0, we measure it after a while. The time is not important here. I'm not trying to make the time important. It is not, just the amounts of internal energy. Then we measure a certain amount here. So finally, our final internal energy will be 20 joules. So what is the change? We're told here, only the beginning and the end value matters. So the change here in internal energy for the first experiment will be 20 joules minus 0 joules, which is 20 joules, okay? We do the second experiment, have the same starting point, is going to have 0 joules. And this time, the next measurement is going to be 7 joules. Last measurement, 20 joules. We don't even have the same number of measurements. Somebody got distracted in the middle. But as long as our final point and our initial point is the same, it doesn't matter what happened in the middle. Delta E for the second experiment, experiment 2, will also be 20 joules minus 0 joules. So we'll end up with 20 joules net, okay? So in state functions are a unique kind of measurement in thermodynamics where the value that you get from different experiments end up being the same value, as long as your initial and the final conditions are the same. So the result or the number you're working with only depends on the initial and final condition, not the process used. As long as the starting point is the same and has the same number, and the ending point is the same and is the same number, you can mess up in the middle. I shouldn't say you can mess up, but you can kind of detour and come back and you get the same value. Okay. Before I move on, I want to give you guys additional examples of this state function because it did help me when I was a student. Okay. So what are some other state functions that we have been dealing with this whole time that we weren't even aware of? State functions. I can't spell sometimes. I have these moments where my brain just stops working when it comes to spelling. Okay, state functions. More common ones. Delta V, delta E, the one we just saw, delta G, delta H, delta T, delta S. Okay, these are the ones I can think of off the top of my head. What do you notice about the format of how these state functions are written? I'll give you guys a moment. Okay, moment passed. They all have delta, that's the change, and it's capitalized delta, right? And then capital letters for the function. So it's delta and capital letters, okay? So the way you measure delta V is V final minus V initial. The way you measure that, this stands for volume, by the way. The way you measure delta E is E final minus E initial. And this stands for internal energy. The way you measure delta G is G final minus G initial, and this stands for Gibbs energy. So remember, internal energy is the total energy inside a system, total kinetic and potential energy. Gibbs energy, we'll learn later on, 1412. This is useful energy. This is the energy that's associated with work. Okay, so apparently not all energy is useful. Not all energy can be converted into work, but Gibbs energy is the maximum amount of energy that can be used to do work. H final minus H initial. This H is essentially energy in chemical reaction or in bonds or chemical reactions. Delta T, temperature final, temperature initial. This is just temperature difference. Temperature. And then S final, S initial. This right here is energy due to randomness. Randomness. Isn't that random? I wanted to say that. I know some of the things I say is corny, but I earned the right to be corny. Okay? So yeah, these are the different state functions. And is this a comprehensive list? But no, but I feel like this is a huge list, and so it should cover most of the things you will learn later on. So let's go ahead and move on from here. So here we're seeing that we can measure the internal energy of the system. The internal energy of the system can be influenced by knowing the heat transfer and the work done. So energy is exchanged between the system and the surrounding. We've said this so many times, but it's done through heat exchange or through work. Heat transfer or heat exchange is Q. Q is heat transfer. And then work, well, that's just work. So we're told here, Q and W are not state functions. This is with passionate, not state function, right? We know they're not because they don't follow the format of state functions. This is definitely a state function. Those are not. What does that mean? That if you change the process when you're measuring Q, you will end up with a different number. If you change the process when you're measuring W, you end up with a different number, okay? These values depend on the process that's being used. So you end up with a completely different number. Okay. Internal energy of the system is the sum of the heat transfer and the work done. So once again, systems surrounding, they're exchanging energy either by heat transfer. They kind of have to be, well, They can be in contact for that one. They have to be closed or by work done. So here you want to make sure you know the signs for heat transfer and work done. So once again, years ago, I remember my journey because I had a lot of moments of just aha, I finally figured it out. And a lot of moments of this chemistry is not for me, right? Because I'm not getting what is going on. It was hard for me to latch onto thermodynamics concepts. So what I did is I tried to find something in my life that what I was hearing sounded like. And then I tried to compare the knowledge I had to the knowledge I was getting to see if there was a correlation. And guess what I found? Money. Heat transfer is like money transfer, right? But I was doing this when I was in the middle of school and I didn't have money. I didn't have money, I knew how money transferred worked, right? So of course, I made myself the system because y'all know how I tell these stories. I made myself the system. And if I was gaining energy as a system, it was synonymous. It was similar to, me gaining money as an individual, right? So here, we're trying to look at the two ways to influence internal energy of the system. It'd be like two ways to increase the balance in my checking account or in my account period. I can take it in the savings too. Okay. So one way is when the system gains thermal energy. So when the system gains energy, that's a positive. Okay. So here's where I was like, since I'm trying to build a backstory. Okay, so I get a no, loan is not positive. I get a scholarship, that's positive. I get a paycheck, that's positive, right? Somehow I'm gaining, receiving energy, thermal energy through contact, right? These are all positive because it's coming to me. This is energy coming to me, adding to my account, right? Ka-ching, ka-ching. And then this part here is saying work done on the system. So once again, you're the system. Maybe getting a massage. I don't know, getting your nails done. Someone is doing the work, not me. I'm not spending my energy. They're spending their energy on me. Work is being done on the system. Positive. So if both work is being done on the system and the system receiving heat, then both of these result in overall flow of energy into the system. So two different ways in which this is contributing to the system. Okay. And so once again, these are positive, positive. See, tying this to money really helped me grasp the concept. Okay. Now when it comes to losing energy, when the system loses thermal energy, this is like, so y'all, disclaimer. In no way am I saying paying bills is bad. But if you have to spend your money, your account, like in the bank, it will show negative. That means money gone. The account is not saying negative because it's a bad thing. That's just the accounting system, right? So it's neither good nor bad. It's just the system. So when the system is spending energy or losing energy, that's negative because you're using the energy from your reserves, right? Losing energy to the surrounding. So it's like giving away money from your account. Negative. Paying bills. Negative. Okay. And then work done by the system. Once again, it costs energy to do work. So if you are the one now out there doing work, energy has to be done by the system. So it's going to cost you, work has to be done by the system. So it's going to cost you energy. So if the system is doing both the work and giving away energy through thermal flow or contact or transfer, then you have an overall negative flow of energy. And this is going to be out of the system, right? So energy flows out of the system is going to be negative. Okay. So here's the question. How do we answer this? A system absorbs. So absorb means coming in. So I'm going to put here plus 250 joules of heat and does work. So you're absorbing heat and doing work. So if you're doing work, it's costing you energy, 23 kilojoules on the surrounding. What is the change in internal energy of the system? So internal energy is equal to heat transfer plus work done. Heat transfer is positive 250 joules. Work done is going to be negative 23. Oh, this is kilojoules. I missed that. Kilojoules. About to say the switching unit. Kilojoules. So this should be 227, I think. Yeah, kilojoules of change in energy. Okay, and then we have heat capacity. Heat capacity is the quantity of heat absorbed. So heat capacity is the quantity of heat absorbed. So when a system absorbs heat, its temperature increases. Okay, so hopefully you got this part here. Let me go ahead and move on. The heat capacity is the quantity of heat or energy absorbed. So we know that different materials absorb energy at different rates, right? Some materials, you expose them to energy and bam, they get hot. Other materials, you expose them to energy and they're resistance of the change. They're like, yeah, I'm in the environment where it's hot, but I will not change. So when a system absorbs heat, its temperature normally increases. So absorbing heat or heat transfer is Q. Temperature increasing, that is change in temperature. So we're being told that there's a correlation between heat transfer and temperature change. The increase in temperature, delta T, is directly proportional to the amount of heat absorbed. In other words, amount of heat absorbed is proportional directly to temperature change. So in the world of chemistry, when we want to, this, by the way, is called an expression. When we want to replace an expression and get a usable form of the expression called the equation, we just replace the proportionality sign with an equal sign, normally an equal and constant. So Q proportional to delta T becomes Q equal to, the constant here is C delta T. So this form here is a usable form called the equation. And that's a more usable form. It's hard to solve for unknowns when you're stuck in expression form. An expression kind of shows you the trend, right? The relationship. Okay, so now we're bringing in a concept called heat capacity. What exactly is heat capacity? Told that the proportionality constant is called the heat capacity. That's this right here, the constant from the proportionality sign. Without defining it, they're telling you how it works. The larger the heat capacity of the object being studied, the smaller the temperature rise will be for a given amount of heat applied. Okay. So, well, they didn't define it. Oh, they define it all the way down here, but not really, kind of define it here. The specific heat capacity, which is different from heat capacity, is the amount of heat energy required to raise the temperature of 1 gram of a substance. Okay. Now the definition they gave us, I don't really like that very much. I like this definition better. The heat capacity is the amount of heat required to raise the temperature. This is the same as the other one. Of a substance. Sorry, I don't have space to write. By 1 degree Celsius. This is the definition I just gave you that I don't like. Let me tell you something. You still have to know it though. I still memorized it because I was supposed to know it. But let me tell you the implication of that. I mean, you know the definition, so what? What does that mean? Okay. If an object has a high heat capacity means greater ability to withstand change in temperature or heat. So this chemical can be in an environment where it's very, very hot. If the heat capacity is high, this object will remain cool, even though its environment is very, very hot. Well, that can be a good saying. Be like an element that has a high heat capacity so that when things get really high or hot, when the environment you're in gets very hot, you remain cool. That would make for a great t-shirt, right? But people will be like, wait, what? What's the heat capacity? And then you put another definition so you can tell them what it is. Anyway, let me get back on task here. So I'll tell you this moment in my life where this heat capacity stuff became real. Okay. So years ago, I was getting married, and then my coworker said, oh, by the way, this is not knocking Walmart. Walmart is my store. When I first came to America, I was like, I love this store. It's so great. You can buy everything here, almost everything. Okay. So my coworker said, don't get a registry from Walmart, because she knew Walmart was my store, for your wedding. You should do nice places like Macy's, whatever. And then she says, Williams Sonoma. You should do Williams Sonoma. I'm like, what is that? So I go and Google Williams Sonoma, and I'm like, wow. At first, because she's like, if you do a registry at Walmart, I will not shop there. And I was like, okay. So I told my husband, we're going to Williams Sonoma. We're doing a registry just for her, because apparently Walmart is not good enough for her. It's her money, right? So I'm like, okay, fine, we'll go to Williams Sonoma. So we go there, and it's this really fancy store. I'm like, whoa, I don't even know where things are. So I go to the server over there, the guy that's working in the store, the clerk or whatever. And I tell him, okay, so I'm like, everything is so pricey. Let me put some pans here. So I'm asking for a cooking pan. So I'm going to draw a picture of a cooking pan right here. I'm thinking it's the regular stuff that we saw at Walmart, or, that the videos they show on TV, a cooking pan. But this cooking pan is so great. So this young man who is showing me the cooking pan, he's telling me, oh, this is for your wedding. Let me tell you this. You should consider this cooking pan. And does this young man proceed to tell me the metal they used to make the pan and why that metal was used? Because it conducts heat very well. It's able to transfer heat evenly into the pan. We use this metal here. It was formed using this whole process. This guy went to explain to me the concept of heat capacity. I'm watching this guy like, they don't do this for me at Walmart. At Walmart, when I'm trying to figure out where is the pan, they can't even tell me what aisle it's on. I'm like, ma'am, where is the pan? I only work in this section right here. That's Walmart for you right there. This guy not only knew where the pan was, the cooking pan, he knew what metal was in the pan. And he proceeded to break down why the metal was used and why a different metal was used in the handle. Did I know chemistry? Yes. Did I know all this stuff was intentional? No, I didn't even think about it. Who thinks about that when you're cooking? When you're cooking, you're hungry, right? But the gist of it was this. They use the metal on the base and the body of the cooking pan with a lower heat capacity, right? Why? You want this metal here to allow heat to flow from the stove into your food to cook it, but not to flow too fast or too slow, just right. So they test a bunch of different metals, right? Do I remember what he chose? I think it was copper or something. I wasn't really focused too much because I was so overwhelmed and too excited. When I get too excited, I can't even think straight. So I'm like, this is so deep. And then he said, for the handle, they chose a metal. And by the way, the base wasn't just one metal. It was layers of metal, some for durability, some for conductivity. I was like, wow, this is deep. And how much is this pan? I think the pan by itself was over $100. I said, you know what? For all the metals y'all use, I think it's worth it. The handle had a higher heat capacity. So for this handle with a higher heat capacity, when the body of the pan is getting hot and cooking your food, right? The heat will transfer through the body of your pan. But when it gets to the handle, there will be less flow of, the metal won't get very hot because remember, it has a higher heat capacity. It has higher tolerance for the heat without the metal itself getting warm or hot. So this will remain cool to touch. And I was like, oh my goodness, I have pans at home. Now listen, Some of my pants from Walmart do this, but nobody took the time to explain it to me. That was my point. I'm looking at this guy saying, really? So since then, when I use my pants and I don't have to use a pot filler, or not filler, a pot holder, yes, but I don't have to use it, I appreciate that the scientists chose a metal with a higher heat capacity for the handle. I appreciate that. Oh, side story. I have a cast iron. And when I was getting the cast iron, they said, oh, this whole uh cast iron pan is cut from one piece of metal. I'm like, oh, that's beautiful. Well, guess what? One time I touched the handle and I write about burnt the inside of my hand. The whole thing is one piece of metal. So it gets very hot, but because it gets very hot, it's able to char the meat and give you that kind of crispy flavor on the outside, juicy on the inside, but it tries to do the same thing with your hands, right? So if you use a cast iron, you have to be very careful. It gets very hot. Anyway, back to chemistry. See, I get all caught up with all this stuff about food. So you have heat capacity, and in some cases, the heat capacity depends on its mass. If it depends on the mass of the chemical you're working with, that is now called specific heat capacity. In specific heat capacity, you have to also consider mass. Okay, so back here we have the equation Q equals C times delta T. This is just regular heat capacity. When you're involving mass, it's going to be Q equal mCs delta T. This is now specific heat capacity. Okay, so CS here stands for the specific heat capacity. Now the units. So let me talk about the two heat transfers. So with the first heat transfer, you're dealing with just C delta T. With this one here, the heat transfer has the units joules. The heat capacity has the units joules per degree Celsius. Temperature here has the units degrees Celsius. This is for heat capacity. For specific heat capacity, this is specific heat capacity. You have Q equal mc delta T. I used to call it MCAT because it looked like MCAT, right? Q is also joules, mass here is grams, and then delta T is degrees Celsius. So CS has to adapt. It will be joules per gram per degree Celsius. Okay. So once again, the units can cancel out. These can be equal to each other. The units can cancel out. These can be equal to each other, right? These units matter a lot in chemistry. So you know what question you're dealing with based on the units of C given to you. Okay. Very good. Okay. And of course, you also have molar heat capacity. In the molar heat capacity, the unit will be joules per mole. So you want to adapt, right? In chemistry, while we have to memorize certain things, you also want to adapt to the problem you're working with. Okay, so let me go ahead and move on from here. And in the molar heat capacity, of course, you have Q, which is going to be joules. I'm going to cover that real quick. Joules equal moles times, in this case, CS will be times degrees Celsius. It will be joules over mole degrees Celsius, right? Because the units have to cancel out and be equal to each other. Yeah. Oh, I already worked all this out. So now I have that page over there. I'll skip over that page. Here we have a problem that we're going to be working on. I tried to erase this earlier and it wouldn't go away. So I'm just going to look at the problem here and make sure we have the information below. You find a penny minted before 1982 when pennies were made nearly of pure copper in the snow. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is about -8 degrees. So temperature initial is -8 degrees Celsius, to the temperature of your body. Temperature final is 37 degrees Celsius. Assume the penny is pure copper and has a mass of 3.10 grams. So the mass of the penny is 3.10 grams, and it's pure copper, so you need to get CS. I think, okay, so we have the information here, right? CS, I think, is 0. I need to go back here. I should stop being lazy. CS, copper, 0.385, right? 0. 385 joules per gram per degree Celsius. Okay, we're going to be using this formula here because they have a mass. So Q equal 3.10 grams times 0.385 joules per gram per degree Celsius times temperature final minus temperature initial. Temperature final is what, 37. Temperature initial, -8 degrees Celsius. So this is going to be times 45 degrees Celsius times 0.385 joules per gram per degree Celsius, 3.10 grams Q. Cancel, 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 cancel. Our answer will be in joules. And you know, I saw this guy with the calculator that he found from online, I think. I don't know. But let me see. I don't have a calculator that I can pull out here. But he kept pulling it out all the time. I'm like, dude, I want that calculator. Like it's a virtual calculator, but I don't know how to pull it out. Okay, you know what? Let me just do the math here. 3.10. I wonder if it's a widget, 0.385 times 45. Okay, I'm getting 53.7 joules. Let's see what they got. I didn't really try very hard with that math, but oh, great. And it's positive. So the penny is absorbing heat from the surrounding. Okay. So this is the end of the first video. So this would be the end of chapter 9, part 1. I'll come back and start right here. So I'm going to write myself a note. Start here. Yeah, start here for the next video. Okay, so I'm going to stop this right now.